Good morning, my dear committees and friends. Today, I would like to present on the topic of elastic space. Okay, the problem says there are dynamics and apparent interactions of massive balls rolling, and they say this is often used to illustrate gravitation. And I am asked to investigate the system further. Is it possible to define and measure the apparent gravitational constant in this world? Okay. This system is often seen as analogy in many physics articles to illustrate gravity. But does it features gravity? Oh, I'm sorry. Okay, in case of gravity, it is a k/r² type of force, and many things on Earth works only if this equation is true. Like for the solar system, it follows the k/r² equation. Does our model do? We are going to prove the validity of this model by applying mathematical calculations. This is how I view it. From the gravity well at first, we will view it from top. You will look from top view. It will be seen as a two-dimension thing. The center, the ball in the center, and thank you. There is a ball in the center, and I will release a test particle, which I call little m, from different radius. The radius is measured from the center of this ball to here. We will view it from top, remember. These are my instruments, and okay, how I set it up. There is a stretching cloth I'll use as my membrane, and I tie it to a big bowl as a frame. And I put a metal ball mass, I will call it big M, in the center. And from top view, we look down as 2D. I measure the distance as 150, 70, 90, and 210 millimeters. I mark it. Then I release my test particle. If we view from top, we will see as if the little m is being attracted by big M, right? If you view it from top. Here I record the time it takes for little m to move to big M. Now it's my analysis. First, I assume that G is a constant because I think of, let's say, on this building, this floor, little g is 9.8. If you go downstairs, it's also still 9.8. So at first, I assume that g is a constant over all r. And so I can use this equation of constant acceleration. I can calculate small g from this thing. And as the equation says this, gr² must be a constant. Remember, here we assume g is a constant at every r. After measuring my time, I get that gr² is not a constant. However, gr somehow gave a constant, and it happened for all of my 4 masses. And this gave me an idea that maybe it's featuring an infinite cylinder system, because in this system, this cylinder goes on forever. The force acting is gmm over r. So here gr is a constant. We are going to find out whether our model is featuring an infinite cylinder or not. Okay, now please look at the other paper I gave you. Okay, this is the equation of motion. This is acceleration. For an infinite cylinder, gravitational, the acceleration will equal mu over x. X in this case is the distance r. Mu is a constant. There are ways to solve equations, and at last, for a infinite cylindrical system, here I integrate from 0 to t. 0 is the time starting. We start at time 0. It finished at time t. And we, sorry a little. If this is the radius of my big ball, and this is my test particle, I told you from the first time that little r is this way. So the distance, when we release it from here, it will travel until here. So we are integrating from small r to big R. These are mathematical terms. And at last, mu in this system will be equal to pi r squared here, 2t squared, and Earth is a kind of function. All right. Now go back to my slide. It means that if mu is a constant at every r for each m, the model is featuring an infinite cylinder. Let's see if mu is a constant or not. And these are my results. At distance r of the first mass, mu gives a value of 14. Same for the second one. There are some of errors, but it's resembling values. Same for the third and the fourth. This kind of proof that mu is a constant. The mu being a constant is kind of showing that our model is featuring an infinite cylinder. Here, mu is a constant for each mass, so we are showing that it models an infinite cylinder. So big G, small g can be calculated for mu over r, as in the reference page, and big G can be calculated from mu over m. These are my results. And these are the units if you want. Here, you remember when I mentioned about g, is small g, is it a constant or not? When I say on this building, this floor, it's 9.8. Downstairs, it's 9.8. You go up to the 30th floor, it's 9.8. But that is when the radius, you compare the height of the building to the radius of the earth, the difference is very small. But you see in my model, the radius of this, small r and big R, the ratio is very different. So in this case, little g shouldn't be a constant. And I found out that as distance increases, little g decreases, and the gravitational constant, it is a constant. So if you might not follow it, I will make a conclusion on what we have talked all about, okay? At first, I assume that g is a constant, okay? Then, if it is a constant, then gr should be a constant. However, I found that gr squared is not a constant, but gr is. Here, I'm not concluding, okay, that it is an infinite cylinder system. But I'm asking that could it be possible to be an infinite cylinder model? And after showing that mu is a constant, you say, where's mu? Mu is solved from the equation of an infinite cylinder thing. So if mu is a constant, yes, it kind of shows that our modeling is fitted into this equation. If we can find mu, we can find small g and big G. So my conclusion is, looking from a 2D aspect, from top view, the model doesn't feature the Earth's gravity, but it is a very good illustration for an infinite cylinder, and I'm able to find small g and big G. Okay, thank you to dear teachers and family.
Okay, thank you for your presentation. So I will going to start with
Yes.
some kind of force that you mentioned as the force, the gravitational force equal to gmm over r squared, right?
In case of the
And
round
then,
object, yes.
yes, and then you taste that the gr squared is not a constant. So this at this point, do you think that do you have any idea why it's not a constant?
The reason that it's not a constant because the equation is wrong. That equation cannot be applied to my model. That's why the number doesn't fit.
So when here we are in our Earth, right?
Yes.
So there are also the gravitation from our Earth.
Yes.
So do you think this is why it is not constant in your model?
You're asking that why doesn't my model follow the Earth equation? Is that your question?
I mean, when you measure gr squared, it is not a constant because there is some effect from the real gravitation from our Earth.
Yeah, I see what you mean, but when at first we did the experiment, let's see, from here, then everybody knows that if you look it as a normal human in 3D real world, the thing that makes little m drop down, it is the Earth's gravity. Everybody accepts that, right? But the model is to illustrate gravity. If like that, why is the reason to use a mass here? It is impossible for this mass to have an attraction for another mass, except it is the work of the Earth's gravity. But the reason, that is why I need to look it from 2 dimensions, so then we ignore we don't know what is the real force. We will ignore that part, but we will pay attention that it's just like a mystery that, okay, some force is acting and the force is from here.
Okay, I got your point. And then as you see from this picture, you measure the value of r as something like a ruler or
ruler.
So I think so when you look at the membrane of this phenomenon, you can see that it's maybe something like this, right?
Yes.
So you measure.
Move to the left. Sorry.
Okay. So if you measure the distance between these 2 points, it's not exactly its distance between this ball and the massive ball here.
Yes, it's not.
So
it's not.
Why? I mean, do you think can we find the distance here, which is the real one?
This distance is the real distance that it travels, but we cannot forget our concept that we are looking from top, and the distance that we view it is, if you look from top, the only thing you see is this. And it is like you're seeing
Yes.
this thing being attracted here, and you don't know what force is acting on it, and
Okay.
the distance is here.
Yeah. So that means when you measure this value, it's already include the error in your experiment, right?
You mean, are there errors in measuring R?
Yeah. I mean, when your model said you measure the horizontal distance,
Yes.
so this already include the error from here.
Error is not from here, but it would be from my ruler. It
Yeah.
is like normal measurement, like there's a length here,
Yes.
and one may say, okay, it's 10.85. Another
So you just look at it, right?
yeah,
No,
yeah.
Yeah.
And
Okay.
there are errors like measuring normal objects.
Okay. Um, could you go back to your infinite cylinder something about the
Yeah.
gravitational force?
Okay, a moment. This one? Yes.
Yeah. So, at the beginning, I think that you told that the force equals GMM over R.
Yeah, force equals GMM over R.
What is that?
Because
I mean, how the difference between like the Newton law of gravitational force
and this one,
Yes.
right? It is a completely different system. In Newton, like the Earth, let's say the Earth and the Sun. This is a round object,
Yes.
right?
Uh-huh.
So you can, one easy way to see that is it different, you can see that if this goes on forever, it has a cylindrical symmetry,
Yes.
meaning that if you are here or here, it looks the same, right? But
Yeah.
for this, if you are here and you go up here, you will see something different. But between you're here and you here, the thing looks the same. You can see this is one distinction. Because the object is different, so the equation that comes to match is different. Is this your question or no?
Yep. I mean, at this point, why you say that it's different when you look from different position?
Okay. Let's say if there's a round object here, and you look down, you are here. Okay, this is you. You look down here, you will see something like a surface like this, right?
Yeah.
But if you look from here, you'll see a surface here, right?
Yeah. So how the difference when we talk about the gravitational force? When it
is different objects, so the force that is acting on it is different.
when
Yeah.
I'm just curious that when
Yes.
it is the mass, yeah, right? So if we observe it, it will be look the same. In my opinion,
What look the same?
I mean, when that's okay. Okay, maybe later after
okay.
this. Okay. And about your
Equation?
yeah. So you measured only instantly at
Can
any
please?
time, only at the time, at exact time, not right like during the I mean
You You mean this is my mass? I release my test particle and I measure the time. And what is your question?
I mean, when you measure the like the G here,
Which?
I mean
you
in
point?
your table.
Oh. My table. Okay.
So the last question, one short question.
Okay.
Do you care about the elasticity of the fabric? I mean, when you do the experiment, when you repeat, will it be changed?
Okay,
Yes,
I'm afraid that I
change.
have to stop now.
Okay.
Thank you very much.
Gravitational force of the Earth, and about the measuring the like measuring the R distance. It's only on the top wheel, so it's not the exact value of the distance that the ball travel. So I think it already includes some error in it. And like about the infinite cylindrical gravitational force, in my opinion, at this point, I can see the difference between this one. So I think it is quite the same.
Thank you, your reporter and opponent, for your informative data. This is a sense for the reporter. She presents an exactly on problems, and the weakness is she didn't tell us about define the apparent gravitational. And the weakness is she used an equation G mm divided by R in this slide, and it is true is dmm by divided by R square. And in the last slide, she used the PDF file and she showed the equation in the cylinder equation, and I think it is the difficult equation to understand. And cylinder equation now elastic space, she used a sphere, and the equation that she used is that cylinder. It is not make sense. For the opponent, he tell you that the effect from the gravitational for the Earth, and I think so is effect that the gravitational of the Earth, and the weakness of his is the when you see the equation, she used the equation in linear acceleration, but in the surface of her elastic space, it had a friction, and she doesn't tell that she ignore it or not. And is the for the experiment for the reporter, she could expand on experiment. I am curious to understand it, and the weakness is she measure the distance and less data. She measure 4 times, but I think it doesn't make sense to show that the big G can be a constant, because in G in the Newton law is 6.67, and show this, and she didn't tell that why big G isn't same as the G G in the Newton law. And for the opponent, he wasted the time with the theory. He didn't talk about the experiment. And as the student, he taught the elastic space, and I agree with him. When we change the mass, the elastic will change, and she should change this math. Thank you.
May I ask the reporter?
Yes.
How do you measure your G, the small g?
Small g. I can find mu and from...
No. In your experiment, do you direct measure it? How you direct measure it?
How... in the reference paper, G is equal to mu over R, right?
I mean from your experiment.
Yes.
Can you determine G?
Small g or
Small
big?
g, small g.
Small g is equal to mu over R. I know mu, I know R, I find G.
How you know mu?
Mu is equal to, as the equation I showed you in the reference, mu is equal to pi r squared over 2t squared earth in the reference paper. Can you please take a look? I can't remember the equation.
And t is the time that so you measure the time.
Yes,
And
I
you
measure
measure
the
the
time,
radius?
I measure the radius. I can
Okay.
find mu.
But if,
Yes.
forget about the mu,
All right.
go back to your slide, I don't know, the analysis page.
Analysis.
Yes. Yeah, 13.
13.
Right. So is that the same G in here?
No. You remember my last slide here? When I assume that G is a constant and GR squared should be a constant. The slide 13 is just gave me an idea. That was just an approximation to give me an idea that can it be possible to be fitted into an infinite cylinder model. That assuming G is a constant, this should be, GR squared should be a constant. GR is not. This assumption is wrong.
Okay. I mean, for your direct measure, can you verify it? Using tracker or whatever that you can track it, right? And you can see that from point to point
I don't
your
have
acceleration.
tracker.
So you don't have the tracker. Then you should have.
I don't have high-speed camera.
Okay, then another one that you should have.
Oh, it's expensive.
You say that you assume that G is constant, and then in your model you assume G R squared should be constant. According to equation, GMM over R squared equals mg.
Yes.
So GR squared would be big G times m.
Yes.
In this case, it doesn't depend on the mass of the ball that you
No,
release.
GR squared is a constant for each mass.
No, because according to the equation, could you write it down? GMM over R squared equals mg, right?
Yes, GMM over R squared is equal to mg.
And then you will get GR squared equals big G times big M.
Yes.
This means it doesn't depend on the small m.
Yeah, it doesn't.
So in your data, your G depends on small m because you change the masses.
No, I changed this mass.
Oh, you change the big one?
Yes.
Oh.
Yes.
GR squared is constant, then you change the big M, then the big G will change in the opposite way. If you increase big M, then the big G will decrease.
If I increase big M and...
Big G will be decreased because GR squared is constant.
It's not. What the...
So I'm confused now.
Don't get confused.
Okay, maybe. Sorry, can you go to slide again? I gonna be a bit harsh here. So let's look at the slide.
Which one? This?
Yeah, this slide. No, don't move. Go back to the same one.
This?
Yes. Don't, yeah.
All right.
So let's follow from the start. The first box. You
Yes.
say G is a constant. I mean,
assume.
assume G is a constant, and you
Yes.
say that with the result of this, GR square should be constant. Why is that? Because
Assume G is a
G already a constant. R is not the same, so it should not be constant,
No, I mean
right?
G. Okay. I see. I mean. Okay.
Okay. Yeah, I think. I mean the.
Okay.
Yes, you understand. So now let's go back to the analysis slide again. The 13.
That is a wrong assumption.
Yeah. So
Why?
so I think you agree now. I mean that G is not constant, right? So but you start with S.
Oh, okay. I'm sorry. If I assume that G is a constant.
No, don't assume. I mean, talk about what you believe now. So G
Okay.
is you believe that now G is
G
not
is
constant.
not a constant. Okay.
Okay, right? So now let's start from that equation again from your experiment. So S is this equation,
Yes.
right? But this A has to be a constant
Constant acceleration.
so that you can use it.
Yes.
And you do experiment based on this one. So could you explain why should I trust your experiment?
This one is when we made the assumption that G
Yeah.
is a constant.
Yeah, I mean, you
So-
measure the G with assumption that is,
So I use this equation,
and
right?
then I should not trust the rest of your experiment, right?
The last result is from the reference paper. That one I integrate, and G is not a constant. Okay, when you say here G is a constant.
Because your calculation, I mean the experiment measured G.
No, my
Is,
experiment, my data, what we know is T and R, right? I measure R, I know it. And each R, I know T, right? And from the reference paper, the value of mu is a function of T and R. And this
My question is very simple. Don't go to the
Yeah.
experiment. I mean, don't go to the theory yet. It's all about experiment.
Okay.
I mean, you measure the G with the equation that assume G is a constant.
At
but
first.
you conclude at the end G is not constant. So why should I trust your experimental data because your measure based on that is a constant? So your data measurement is based on the assumption that G is constant.
I erased that assumption away already.
But your data is, when you say GR is constant, that G that you measure is on the based on the measurement is based on the G is constant.
Okay,
right?
I'm sorry. You're missing understood. I might make a. Okay, here I assume, and after I found that, okay, let's say only G, okay, look, only G, not GR squared. G should be a constant, okay, at each R. If it's true, if this assumption is true, small g should be a constant at every R. And in the purple thing, G is not, so this assumption is wrong. We cross it out, okay? And the new reference paper I gave you.
Because your experimental data.
No.
Your equation is based on the G is constant, right? Look at slide 13.
No, that assumption is wrong.
Yeah, I know, but your measure G is on that.
I didn't measure G, I measured T and R.
Yeah, but
Okay, that's why I'm asking is how you direct measure. So maybe you should forget about G. Let's just stick with A, and then you measure A directly from the whatever the distance or the change in the velocity. That's why I'm asking. You can measure it with the tracker, and then you know how the second derivative of the distance that you have. That directly measure the acceleration, and then you can relate it if the acceleration is constant, then you can relate this with g, and then you can prove that a and g is constant or not. If you see that a is not constant, then if when you relate to g, g also is not constant. That's the direct measurement. So you don't have to forget about your theory. Just look at your data and then you measure just by the definition of acceleration.
I see what you mean, but what if I don't have the tool to measure it directly by video?
Then you can find it. You need to find a way that you prove.
If you can measure this far, you have enough tool. I can suggest you later.
So the aim is to let me direct measure. Is that what you're saying?
You do direct measurement and then you try to compare with the theory, not start from the theory and then go to the experiment.
I see what you mean. Thank you.
You can get direct measurement in